All right, happy Thursday, guys. So like the title of the video says, today we're going to be talking about this concept called molarity. Molarity. But I thought it would be worthwhile for us to do a little bit of review first about what we've already learned this week. So, this week we've been talking about the mole. That mole homework is due tonight. And remember that the mole is a concept. It lets us kind of make a bridge from the microscopic world, the world of very, very small things, to the macroscopic world, the world that we're used to with big things that we can see with our eyes. So the mole, it relies on this number called Avogadro's number, named in honor of Amadeus Avogadro. And it's a huge number, 6.022 times 10 to the 23rd. That's Avogadro's number. I've even gotten it all written out really precisely here. It's a huge number of something. Usually we use Avogadro's numbers to count particles. So 6.022 times 10 to the 23rd atoms, or maybe molecules. But they're very, very small particles that we're counting, which is why we can have such huge numbers of them and it still be reasonable. So if we keep looking here, this is just saying that it's basically just a number, just like a dozen means 12 or a trio means 3. A mole is just a number, and it means Avogadro's number, 6.022 times 10 to the 23rd power. On Wednesday, yesterday, we talked about one way that we can use the mole, and that's the molar mass of a substance. The molar mass of a substance is measured in grams of that substance per mole, usually grams in 1 mole. Every substance is going to have a unique molar mass depending on its composition, depending on which elements go into it. We have been doing problems like this since before we went into e-learning. So we should be comfortable with these problems. You use your periodic table. You look for the average atomic mass. You add those up, multiply by the subscripts. I think I have an example in here. Let's take a look. Yeah. So if we wanted to find the molar mass of isopropyl alcohol, rubbing alcohol, we would do that this way. I know that the formula for rubbing alcohol, isopropyl, is C3H8O. So 3 carbons, 8 hydrogens, and 1 oxygen atom. These numbers, these AMU numbers, I'm finding those from the periodic table, which has the average atomic masses of the elements. And I'm multiplying by the subscript. So 3 atoms of carbon, each atom is 12 atomic mass units. That's 36 AMU. 8 times 1 is 8. 1 times 16 is 16. I add up all those subtotals to get 60 atomic mass units. So 1 molecule of rubbing alcohol is 60 atomic mass units. That's microscopic. That's too small. If I bring it up to the macroscopic level, I can say that 1 mole of rubbing alcohol is 60 grams. 60 grams is something much more tangible, something I can measure, and that makes a difference. 60 atomic mass units, it's microscopic. It's so small. It's at a completely different scale. But the math is nice that it works out this way, that we can find the molecular mass, scale it up to the molar mass. So 60 grams per mole for isopropyl alcohol, this C3H8O. So there's our review done out of the way. Let's switch it over to the whiteboard, and we're going to take a look at our new topic, which is molarity. It should be really similar to what we did here with molar mass. So let's kick it over there. So when we think about molarity, the definition that I would give you for molarity is it's the concentration of a solution measured by the amount of substance per volume. So when I'm talking about this type of concentration, I'm talking about how much of something is in the solution. A solution is just like, it's a liquid that is a mixture. It's got some things that are dissolved inside of it, like salt water, for example. So I can measure the concentration of a solution. Maybe I have a solution of salt water that is just a little bit salty. I just dropped a pinch of salt in there and I stirred it really well. It's got a low concentration of salt. Alternatively, I could dump handfuls and handfuls of salt in there and try to get that to dissolve. That would be a very concentrated solution of salt water. So the concentration is just how much the amount of substance is in that solution per volume. So that makes a difference too, whether we're talking about a very small amount of solution or a large amount of solution. I've got our two formulas from this week on the board here. This is one that we've already done, the molar mass. Sometimes we can abbreviate that to mm. The molar mass is equal to grams of substance divided by moles of substance. It'll tell us how many grams are in 1 mole of that substance. That's the molar mass. What we're learning today, molarity, we can abbreviate that as capital M. Lowercase m, remember, is mass. So capital M is molarity. It's the concentration. The way that we measure that is moles divided by liters. Moles divided by liters is equal to molarity. So this will tell us the concentration of our solution. If we have a lot of moles in a small volume, a small number of liters, that's very concentrated. If we've got a small amount of moles in a large volume, that's not very concentrated. It's a low concentration. So in this next little segment, let's see if we can't use this formula, molarity equal to moles over liters, to solve 3 really quick algebra type problems. Eventually we'll need to use molarity in dimensional analysis as well, but let's start with the algebra approach first. That might be a little bit of an easier transition into all this. Alright, so let's see if we can't use this molarity formula to solve a few algebra problems. Eventually you're going to need to be able to use molarity in dimensional analysis, but let's start with something more at this level with an algebra approach. Starting with our blue problem up here. My variable is capital M, molarity. So I'm trying to find the concentration, the molarity of this solution. I know I have 3 moles of substance in 6 liters of solution. These units are going to end up combining. Moles over liters, that's molarity. So I just need to do 3 divided by 6. If I do 3 divided by 6 here, my answer is going to be 0.5. And the way that I would label this is with a capital M. So this is 0.5 molar. We would pronounce this molar, just like the teeth at the back of your mouth. So how concentrated is this solution? It's 0.5 molar, or half molar, which is still decently concentrated. That's still a pretty strong solution. Remember that 1 mole is Avogadro's number worth of particles, 6.022 times 10 to the 23rd. So even just half that much is still a pretty huge number of particles. That's still a pretty strong solution. Let's try this green problem down here next. The setup is similar. I'm still trying to solve for molarity, the concentration. But I don't have quite as nice numbers this time. This is more like one I'd have to put into my calculator. I'm seeing that I have 0.05 moles over 380 milliliters. This is not the molarity formula. The molarity formula has to be in liters. So I'm going to need to change this number down here. 380 milliliters is going to become 0.38 liters. And then if I do my algebra from here, I actually already put this into my calculator. I'm going to find out with significant figures, this solution is about 0.1 molar. So about 5 times weaker than this concentration up here. This is still kind of decently concentrated, but not quite as strong. So 0.1 molar using my significant figures. Let's try this last problem in red up here. I'm looking for a different variable this time. I told you that this solution is 4.0 molar. The molarity is 4.0. I know that I have 800 milliliters of solution. And then my variable is up here in the numerator. I'm solving for moles here in the numerator. When we have moles as our variable, we make it a lowercase n. So n for moles. I don't know why it's n. I don't know why they decided that. But n is the variable for moles. I've got a similar problem as I did in the green problem here. My volume is given to me in milliliters, but I can't be cool with that. I need to convert those into liters before this math will work. So instead of 800 milliliters, let's change that to 0.8 liters. Now my algebra is ready to go. I can solve from here. I would multiply both sides by 0.8. It'll cancel on the right side here. And then whatever this product is, that's my answer for my variable. I've also gone ahead and done this one in advance in my calculator. It turns out to be just about, I'll put approximately here, 3 moles. This is using significant figures. This measurement here is not very significant. So just about 3 moles of whatever my substance is. It's not a story problem, so it didn't tell me what that substance was. But I do know that I have 3 moles. Remember, that is actually a huge amount, especially for a solution that's less than a liter. 3 moles of substance is actually about 2 times 10 to the 24th particles of that substance. 3 moles is a huge amount. It's a lot of particles. If I were to try to write that out longhand, I'm not even sure if I can. Let's find out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and then a 2. It is a massive amount of particles that we're talking about here. This is into heptillion, I think we would call it. Whatever the 7 prefix would be, heptillion particles. So 3 moles. Remember that mole, we can act like it's a dozen. If this said 3 dozen, we would do 3 times 12. But the mole is based on Avogadro's number, which is much bigger than 12. So 3 moles is actually a massive number of particles. This is a very concentrated solution over here. Okay, so we've done the algebra approach now. Let's see what I got coming up next here. It looks like I have just one more example for you here that we're going to do. And it's going to be something a little bit different than what we've done in other video lectures. I'm going to give you a chance for some extra credit points here. Like more than, I mean everything is extra credit now, but more than that. I'm going to give you a chance to get 5 extra credit points just for doing one problem here. So let's take a look at what that is. Alright, so for this last part of the video, I'm going to give you an extra credit opportunity. It's going to be sort of like a story problem. If you can give me the answer, I'll give you 5 extra credit points. So, what I'm going to be doing for this little portion of the video, I am going to make some tea. I like to drink this yogi tea, especially right now. It's good for your respiratory system. But when I make tea, I like to add lots of sugar. So I'm going to add sugar into my tea, and that's going to make a solution. Your job is to tell me what is the concentration of that solution. What is the molarity of sugar in my tea? If you can email me with the correct answer, I'll give you those 5 extra credit points. So watch carefully how I make this, and then you can do the calculations and get back to me. Here we go. Alright, so I need to boil some water first. To measure my water, I'm going to use my super nerdy coffee mug here that actually doubles as kind of like a beaker. It's got little gradations every 50 milliliters. So, I'll measure out a little bit of water here. It might not be totally exact, and that's fine. So that's about 400 milliliters. We'll add that in here. I'm going to go for just a little bit more. Yeah, let's add about 50 more milliliters in there. So, if you're keeping track, the volume of my solution is going to be 450 milliliters. Alright, so next up, I need to measure how much sugar is going to end up going into my tea. I'm going to use my balance for this part. So I'll turn it on. I don't want to pour the sugar just like right on top of this and make a mess. So I'm going to use my coffee mug again. But I don't actually care about the mass of the coffee mug. One thing I could do is I could see that it's 164 grams. I could just subtract that out. But instead, I'm actually going to tare this. If I push that button, it's going to act like the coffee mug's not even there. It says it's at 0 grams. Perfect. Now I'm going to add my sugar. I like to keep my sugar in this little elephant that I got in Tokyo. So I'm just going to eyeball this here a little bit. Getting close to enough here. That's probably plenty. It's probably too much, but... So 19 grams of sugar that I'm going to add into my tea once it's done boiling and steeping here. That 19, oh no, it says 20. We'll go with 19 and a half since it doesn't measure halves. So 19 and a half grams of sugar. The formula for sugar, you're going to need this too, is C6H12O6. 6 carbons, 12 hydrogens, 6 oxygens. And we're going to go with 19 and a half grams since it keeps kind of fluctuating between 19 and 20 grams. So 19.5 grams of sugar. So just to recap, I took 19 and a half grams of sugar and I added it to 450 milliliters of solution. So if you can tell me what is the molarity of this solution, if you can email me with your answer, I'll give you 5 extra credit points. Until then, see you next week.